This is Chemistry, Chapter 13, Lecture 3. In your textbook, we're starting on page 436. And we're going to learn about energy diagrams and also entropy in this lecture. So if you'll start at the top of page 5 in your notes, if delta H is negative, that means an exothermic reaction, to remind you of that. Activation energy, all right, that's a key component of this chapter. Key vocab, it's energy required to start a reaction. Okay, so a chemical reaction is a rearrangement of valence electrons. Since electrons repel, activation energy is necessary for molecules to get close enough to react. So, for example, why is this paper not burning here right in the air? We have plenty of oxygen. Paper burns. Why isn't it in flame right now? It's because in order to start that combustion reaction, we need more activation energy. Okay, so the activation energy could be supplied by a match. All right, and a match, if I lit a match and put it right next to this paper, that would give a lot of activation energy, and the combustion reaction would start. So there's an example of an energy diagram on page 436 that you need to familiarize yourself with. And also, you need to, before we work these on your own problems, make sure that you read through example 13.5. All right, that starts on page 438. And that will tell you pretty much all you need to know about energy diagrams. So let's work on your own 13.8. on page 439. So that one says, suppose you perform two experiments. In the first, you run a reaction that we'll call reaction A. The reaction's hard to start, but once it gets started, it gets very, very hot. In the second reaction, you run reaction B. This reaction is easy to start, but only gets slightly warmer. Draw an energy diagram for each reaction. Okay, so first reaction A. On the y-axis, we have energy. And the unit is going to be in kilojoules. And the x-axis, what the text calls this is the reaction coordinate. But really, that's just time. So we're plotting energy versus time. So it says in reaction A, it's hard to start. What that means is it has a really high activation energy. So that reaction would look something like this. Okay, the reactants are on this side, and then the products is what you make over time. Okay, so we'll start at this energy. In order for the reaction to go, you have to add a lot of activation energy. So that's the difference between the very top of the hill and the left side. And then it gets really warm. So that means if we took the energy of the products and subtracted the energy of the reactants, it would be very negative. So this is an example of a highly exothermic reaction. The energy of the reactants is much greater than the energy of the product. So all of that extra energy is released to the surroundings. Let's try reaction B. Okay, again, I'm just going to label this kilojoules and time. Again, the book would label that as reaction coordinate. So it says in reaction B, it's easy to start. That means it doesn't require much activation energy to get started, but it doesn't get very warm. So it's still exothermic. It just takes a little activation energy, but you see the right side is not much below the left side. This is the reactant side. This is the product side. So not a lot of energy released to the surroundings, so not very exothermic. Okay, so write this in your notes in a spot. if you need from an energy diagram, if you need to calculate by looking at the diagram activation energy, the way that you can get that is you just take the energy at the top of the hill minus the left side. Top of the hill minus the left side. So let's say for reaction A, at the top of the hill, it was, I'm going to get this out of the way here, it was 100 kilojoules. And the left side was at 50. Then the activation energy would be 100 minus 50, or 50. All right? And then delta H, how could I get delta H from an energy diagram? It's just the right side minus the left side. Okay, so let's say the right side on A, the energy was 10. So in that case, delta H would be 10 minus 50, which is negative 40. So the fact that it's negative tells you it's an exothermic reaction. If products were higher than reactants, you'd have a positive a delta H, which would make it an endothermic reaction. Okay, I'm going to erase that, so you pause if you need to, and we'll move on to the next topic. Okay, the next topic is the second law of thermodynamics, all right? And the key concept that goes with the second law of thermodynamics is entropy. Entropy is a measure of disorder, and the letter that we use to signify entropy is S. The unit is typically joules per Kelvin, so energy per unit of temperature. Okay, the main entropy equation, and you're not going to be using this in any math problems, but it's the entropy of the universe is greater than or equal to 0. That means that the universe is increasing in disorder or staying the same, okay? The universe is not getting more ordered, it's getting more disordered. Ultimately, what that means is that heat is traveling to cold. So the heat in the universe is traveling to the cold part of the universe, and so ultimately that's what it means. So the next set of bullets, the solid phase has the least entropy. Liquid is in the middle. And then the gas phase, and liquid also aqueous. All right. Gas phase has the most entropy. So gas molecules are moving really fast, okay? More disorder. All right. And another thing is entropy increases with temperature. If the temperature goes up, entropy goes up. That should make sense because molecules are going to move faster if it's hotter. So faster movement, more disorder. And then entropy increases with number of moles. Of course, this is in your... So the more material that you have, the more molecules that you have, the greater entropy that you're going to have. Okay, so if entropy on the product side is greater than entropy on the reactant side, then entropy is positive. So if you have S of the products greater than the entropy of the reactants, then S is positive. Vice versa, S would be negative. Okay. Okay, flip on over to page 6 of your notes. Pause this if you need to. And let's look at on your own 13.9. And this is on page 443. The instructions are to determine the sign of the change in entropy. So our first reaction says, I'll go ahead and write it out, and we do need to write in the phases. C2H4O2, aqueous, which you can treat as a liquid, plus NaHCO3, which is a solid, and that makes NaC2H3O2, aqueous, plus liquid water, plus CO2 gas. Okay, so what is the sign of the entropy? Okay, gases have the most entropy. The right side has two liquids and a gas. The left side has a liquid and a solid. So that makes the right side, okay, so S of the products is greater than S of the reactants due to gas. Okay, so that means delta S is positive. Okay, if the right is greater than the left, and the right is the only one with a gas, it also has more moles, all right? If you add up the coefficients, you have 3 moles on the right side and 2 moles on the left. But we'll look at phases first. All right, let's look at reaction B. We have 2H2O2. And that's decomposed into 2 moles of water and 1 mole of oxygen gas. Okay, so we've got gases all the way through. We can't look at the phases. So if the phases are the same, what you do is count up the moles. So on the right side, we have 2 plus 1. Use the coefficient. We have 3 moles. On the left side, we just have 2 moles. So since entropy increases with the number of moles, the entropy of the product side is greater than the entropy of the reactant side due to moles. So that means the change in or the delta S is positive. Change in entropy is positive. Entropy is increasing with this reaction, getting more disordered. That's what positive entropy means, getting more disordered. Okay, so I'm going to go ahead and erase so I'm not having to squish part C down here at the bottom. So pause if you need to. Okay, the reaction part C, 2AgNO3 aqueous plus MgOH2, which is aqueous, makes 2AgOH, which is a solid, plus MgNO3 and that phase is aqueous, AQ. All right, hard to see that. Okay, so in this case, the right side has a solid. The left side has all liquids. The right side has a solid, though. So S of the products, the entropy of the products, is less than the entropy of the reactants because we have a solid on the right. So that means delta S is negative. This reaction is getting more ordered. How can that be? Well, a reaction can get more ordered as long as the surroundings are getting more disordered. So the entire system needs to be getting more disordered. But a reaction within a system can get more ordered. Otherwise, you couldn't make solids, could you? Out of liquids. All right, so that is 13.9, how you determine the change in entropy, or at least the sign of the change in entropy. Now let's use our table and determine mathematically the change in entropy. So we are on page 6 where it says change in entropy equation. This is an equation that you'll have to memorize. The change in entropy at standard conditions is equal to the sum of the entropies of the products minus the sum of the entropies of the reactants. Okay, so similar to enthalpy, all right, and we're going to be using table 13.3. So have that ready to go. And you don't want to accidentally use the wrong table on that sheet. There are 4 tables on there, so just make sure you read the title. The title 13.3 says standard absolute entropies. Okay, so no problem. Read the title and you won't accidentally use the wrong table. So let's look at 13.10, and we are on page 444. And we are given the reaction CaO solid plus CO2 gas makes calcium carbonate, CaCO3, and that's a solid. This is the shellfish reaction where shellfish make their shells with lime and carbon dioxide in the ocean. Okay, so we're going to try to figure out the delta S from this reaction using this formula in table 13.3. So it's balanced, and there's just 1 mole of each. We're going to start with calcium carbonate, 1 mole. And looking up calcium carbonate in table 3, okay, it is kind of in the middle of the table, and it's 92.9, and the unit is joules per mole K. And then we're going to subtract out the entropies of the reactants. So 1 mole CaO solid is in the second column of substances at the bottom. That's 38.2. And then we're going to subtract out the second reactant, 1 mole of that, and CO2 gas. The entropy of that is right above CaO. It's 214. I don't really have, well, maybe I can fit that in here. Mole K. I should have started further to the left. So that will be 92.9 minus 38.2 minus 214, which is negative 159.3. And the unit, mole and mole cancels, and the unit is joules per Kelvin. Okay, so remember, products minus reactants, unit joule per Kelvin. It should make sense that the entropy is negative, that we are getting more ordered, because we're going from a solid and a gas to just a solid. So that means we are getting more ordered here. Okay, so that finishes up Lecture 3. Lecture 4 will have the final topic in this chapter. And you should be able to do homework problems through review question number 9. And so you can do review questions 6 through 9 by now. Actually, if you're looking at the previous lectures 1 and 2, you've got enough information to do all the review questions through number 9, and you can do the practice problems. You can do 1 through 6 and also number 9 by now. And we'll finish up. You can actually probably do, let me take a look real quick. I think you can do a few more than that. Okay, on the practice problems, you can do, let's see, number 7 also. So you can do 1 through 7 and number 9 and hold off on 8 and 10. So 1 through 7 and number 9, we'll do 8 and 10 with lecture 4. All right, thanks for watching. See you next time.